Hi, welcome to the final stage of CHUMP, a homemade processor. This stage includes the addition of several new chips, including the multiplexer, the address buffer, the RAM, several NOT gates, a second program counter, the arithmetic and logic unit, the accumulator, a second control ROM, an output register, and finally a second MUX. So what all these LEDs represent, these LEDs represent the first program counter, these LEDs represent the second program counter, these LEDs represent the output register, and finally these outputs represent the accumulator. The program currently running is designed to display a brightness on an LED using pulse width modulation, or PWM, which is similar to that used on the Arduino. Essentially, the way it works is it takes the value that it reads from this bank of switches, and then based on the value, it updates the duty cycle accordingly. So the higher the value of the switches, the higher the duty cycle. So if we put our DMM on, we can see right now that the clock's frequency is running at 90 kilohertz. And so what you see right now, as I tone down these switches, the brightness should decrease of this output LED. And essentially the way it works is not by voltage division, but actually by duty cycle. So if I decrease the frequency, it's now at 1.5 kilohertz as opposed to 90 kilohertz, we can see that the LED is actually flashing, and based on the value on these switches, the duty cycle will change. So right now, it's on for a very short period of time, but it's off for most of its time, whereas if I put all the switches on, it's on for a long period of time and off for a short time. And then when the frequency is tuned up, this correlates to changes in brightness. So essentially the way that this CHUMP sketch or program works is it counts from 0 to 16, and then it turns off the LED at 0, and it turns on the LED at a flag. And the flag can be set from anywhere from 0 to 15 using this bank of switches. So when the flag is set to 15, the LED is on from 0 to 15 and only off from 15 to 16. Whereas when it's set to 1, as in this case, the LED is only on from 0 to 1, and it's off from 2 all the way to 16. By running the clock at 70 Hertz, we can see why the clock needs to run so fast to begin with. When I start the program, it takes a full 10 seconds for this LED to come on, which means one period of this oscillation is quite long. So in order to achieve persistence of vision, the frequency needs to be extremely high. So this is the Chumpany's program that was running just a second ago for PWM brightness control. Essentially what it does on a very high level is it sets the output register equal to 0, it sets a variable called I equal to 0, it increments I, then it checks if the sum of I and the input register or banks of switches is equal to 16. If it is, it bypasses the else clause and sets the lowest bit on the output register or turns on the LED. If it's not, it increments I again and continuously checks it until the sum of I and the input register is equal to 16, at which point it bypasses the else clause and sets the bit to high. Then it continues to increment I until I overflows to 16, and then turns off the LED by starting back at the beginning and repeats the cycle. When the clock runs at 90 kilohertz, this happens many times a second, which creates a persistence of vision effect and allows the LED to have its brightness controlled. So on a lower level, the way it works is it stores a 0 into the accumulator as well as the output register. Then it stores the 0 to address 1, and address 1 becomes variable I, and then it increments I by loading into the accumulator, adding 1, and storing it back to its address. 1 again corresponds to I. Then the program loads the value on the input register into the accumulator, adds I to it by reading from I, which is address 1, finding the sum of the port, which is in the accumulator, and the value in address I. Then it checks if the value is 0, which means it overflowed, and each branching instruction is preceded by a read instruction in order to set the second program counter, because CHUMP runs on a 4-bit bus but has an 8-bit program counter, so it needs to set each 4 bits independently. When it reaches the flag or when the sum of I and the input register is equal to 16, it orders the value in address 0, which from the top is the value in the output register with 1. By doing a bitwise OR, it guarantees that the LSB will be 1, and it keeps the rest of the bits intact. The program then continuously increments I until it resets back to the beginning, and again repeats it many times per second. This program uses all 4 inputs of CHUMP, but it only uses 1 output of CHUMP. Additionally, it only uses a total of 27 lines, although this version of CHUMP does have a theoretical maximum of 256 lines of code. Thank you so much for watching, and that concludes the CHUMP series. Thank you.